This is slide 26. You can read 25. As I said, you should read on your own. I mainly explain some of the figures, tables, and diagrams. So here, I'm explaining this one. This is called latch. This is called an RS latch. R is set, reset, S is set. If you look at the truth table, when they are both 0, your output has no change. When R reset is 0, but S is 1, the output is 1. When you want to reset the input, it will always reset it to 0. They cannot both be 1s at the same time because you cannot set and reset at the same time. So that is forbidden. Let's look at how this works. Okay, S is 1. The first time, for example, and there is no input from Q because it's the first time, negated, it becomes a 0, P is 0, 0 coming in, and R is 0, 0 coming in, and negated, it becomes a 1. So now that 1 comes back as a Q. And that Q is 1, S now there is no new input, S is 0. So 1 negated becomes 0, 0 negated becomes 1, and it will forever be 1. So if S is 0, then it will forever be 0. You can test this on your own, you can trace it. But what this is doing is because it uses this feedback, okay, it feeds back to the circuit, it becomes a memory element. So if S is 1, if we don't reset or we don't do anything, then it becomes a 1 forever. This remembers the input, which is 1. That's why we call this a memory element. This is called a latch. Now, if you go to the next slide, here, this is called a clocked RS flip-flop. So when you add a clock signal to a latch, it becomes a flip-flop. That's the difference. A latch does not have a clock signal, while a flip-flop has a clock signal. This is the D flip-flop, data flip-flop. So if you look at the truth table, when there is no clock signal, then the output is whatever is on the bus. It's constant. When there is clock signal, then it will output whatever the data is. And this D is data, the C is clock signal. And you can read this slide on your own. Registers are made of flip-flops. And so if you have a 32-bit register, you will need 32 flip-flops. If you have a 16-bit register, you will need 16 flip-flops because each flip-flop can only remember 1 bit. This is slide 34, this TriState gate. TriState gate, it functions as a buffer. Whatever the input is, it is on the bus, but it's not flushed out until the enable signal is here. So when this enable is set to true, then the input, this signal will be the output. That's what a TriState is. And let's just look at the difference. I wrote it here. You can read that. That's the difference. Now, if you look at this registers and buses, this diagram, let me explain this. So you have 4 registers, 0, 1, 2, 3. And this C0, C1, 2, 3, these are clock signals. And these are the enables, the TriState. So whatever signal, whatever value you have in the register, they are here, okay? But they are stopped. This is like a dam. it's blocking it from going onto the bus. Only when this is enabled, it's set to true, then the data will be flushed to the bus. And then from the bus, it will come here. Depending on which clock signal is on, it will go to that register. In this figure, let's look at how this works. So you have 4 registers and you have 4 clock signals, and then you have these enables, and then you have, this is the source decoder, this is the destination decoder. That tells you what is the destination, which register is the source, which register is the destination. So here is the instruction register. It only has 4 bits. I'm giving you an example. Suppose my instruction register contains 1101. The first 2 ones are the destination bits. So they are 1, 1. We should not negate them. We should just follow these ones. It comes here to register 3. It also goes to register 1. But we need to look at this bit, R3, the 3 bit. And this one, it goes to register 3, but it doesn't, it goes to register 2. It doesn't go to register 1. So when you have 1, 1, you are only, your destination register is register 3. What about the source decoder, the source register? I gave you an example as 0, 1. So this is a 0, right? And then we need to negate it to make it a 1. So we should go this path. 1, it doesn't go to this one, not this one. It only goes to this one and this one. So only register 1 or register 0. That's this bit. And this bit, since it's a 1, I'm giving you a 1. It comes here. We do not negate it. We just follow the true path. It only goes here. So it goes to register 3 and register 1, but this bit only goes to register 1 and register 0. So register 1 is the register, the source register. So we enable the source register, get the data, send it to the bus, and then it comes here and it goes to register 3. So this is going from register 1 as the source register to register 3 as the destination register. And I gave you these codes here. That means which register is the destination register. Okay, these 2 bits represent the destination register. For this diagram, for this table, this figure, you have 3 buses, bus A, bus B, and therefore you have bus A enable, and this is enable for register 0 on bus A, and this is enable for register 0 for bus B. Those are the signals there. And the data, if they're enabled, they come here to ALU. And ALU has 2 bits as the function code. 2 bits, 2 to the second gives you 4 functions. So you can only perform add, sub, and OR. And then you have instructional format. Oh, okay. And then you have these enables. The result from the ALU will go on to bus C, and depending on which register is the destination, it will clock that register. So if you look at this format, this instruction, this is the function code, opcode, that's the ALU code. And this is the enable for R0 for bus A, bus B, and R1, bus A, bus B, etc. And these are the clocks for the destination register, which one is should be the destination register, depending on that. So that is how you understand this payable, this figure.